clearly one of the big challenges of this question is there's just so much information. This is a theme that you will see throughout all of mathematics, that our brains are only so large, right? It's the reason why you can't multiply 5-digit numbers in your head. There's nothing difficult about multiplication, or the addition that comes with it. There's just too much of it, and that's why if I gave you paper and a bit of time, you probably could do 5-digit numbers in your head, right? Because you would break it down into a series of smaller problems, and then you'd be fine. This is like a pair of 5-digit numbers that you've got to multiply in your head in its current form. So what I want to do, again, something we've seen all the way throughout this course, is try and break up the problem into smaller pieces. That's what I've got down here, okay? Now, do you notice we've got triangles, we've got quadrilaterals flying everywhere. They all overlap. That makes it challenging. So what I've pulled out is just triangle ABC and triangle ABD. I've pulled them both out because they share this common side here. And we've already noticed in this course before, if you can look at the same object from two different angles, you almost always gain insight. So, I want you to look at ABC for a second. ABC. There are some lengths in this diagram ABC that I haven't put on there. They come from the original one. For example, BC. You see how it's got F in this spot here? What is F in relation to BC? What is F in relation to BC? It's the midpoint, right there. That's how it's constructed. So I'll just label those in. Maybe you want to have this supplementary diagram in some corner on your page as well. But AC is also a similar relationship here, isn't it? Can you see where AC is? Can you see where AC is? And so K is, it's a bad diagram here, but K is also the midpoint of AC. Do you see that? I think I labeled that as 6. Okay. Now, think back to the first property we proved today. What does that tell you about FK? We've got these similar triangles here, which means that FK must be parallel to the third side. Do you agree? It's the interval that joins the midpoints, and so it's parallel to the third side. Okay? So we know that this is true. But now come over here. Isn't this deja vu? There's a lot of deja vu in this diagram, okay? BD, what is BD? It's the diagonal of the big quadrilateral, right? And we form L by bisecting BD. In exactly the same way, AD is right down here down the bottom. It's also been bisected. So tell me what you know about AB and LH. They're parallel. But what I want you to notice is they're both the same parallel. They both have to be the same parallel because look, AB is the same side in both triangles, right? So what does that tell you about FK and LH? They're parallel as well. So you see, by looking at it the same side, this guy, from two different, can you bring it over to this big diagram now? You can see that this is parallel to this, but this is also parallel to this. So they are parallel to each other. Does that make sense? Okay, I can rehearse this argument. I won't redraw it because it's the same thing as over here. I can rehearse this argument for FL and KH. Can you see the triangles that they live in? What triangle does FL live in that I can use this relationship with? Yeah, I can see it. BCD, it's that big one over there. So you can see that this side is going to be parallel over here. Do you see it? Because it's been formed by joining the midpoints of BCD. So here's the third side. But this third side is in another triangle. Do you see it? What's it called? Yeah, you see it. You're starting to see through the diagram to the structure that's there. A, C, D, it's the same deal. Zoop. Like so. Okay? So now we know that this guy is a parallelogram. In a parallelogram, we know that the diagonals bisect each other. This is a property we learned like a couple of years ago under quadrilaterals. Okay? So this tells us, number one, that F, let's give this guy in the middle a name. Let's call him O because he's right there in the middle. Okay? This tells us that firstly, F, L, H, K is a parallelogram. I won't write all the reasoning out because we just talked through all the reasoning and you can put all the letters down yourself. It's a parallelogram, therefore, what can we say here? FO equals OH and KO equals OL because diagonals bisect each other. In a parallelogram, that is. They don't always in all quadrilaterals. So that's really nice. Where can I go from there? Well, do you remember the very first construction you made? You can see I've got these orange diagonals. This guy here has been created by joining the midpoints of the biggest quadrilateral that you can see. So if I look at EFGH, clearly what kind of shape is it? It's a parallelogram, just like we did before. Okay? So if it's a parallelogram, then what does that tell you about its diagonals? They also mutually bisect each other. Now, they share a diagonal, these two quadrilaterals I just looked at, the red dotted one and the orange dotted one. Sorry, red and orange. That was a bad choice on my part. But you can see, if they both mutually bisect each other, then I've got EO equals OG in this bigger parallelogram. So I'm going to say EFGH is a parallelogram for that reason over there. Therefore, EO equals OG. Now, if these two parallelograms mutually bisect, they have mutually bisecting diagonals, and they actually share a diagonal, then all of them have to bisect each other all at that one spot, which is what your original construction proved in the beginning, or showed anyway. Okay, so I'm done. There you go. We proved it. It looked like a disaster to begin with. In fact, I'd say it probably looks more like a disaster now. But you can see through the structure now because you recognize shapes in there that you wouldn't have been equipped to see before. Okay?